Hello, everyone. My name is Oded. Today, I'm going to talk to you about scaling infrastructure in a modern cloud environment. I'm the CEO and co founder of DragonflyDB, the most efficient in memory data store in the galaxy. I've been building scalable infrastructure for the last 25 years. Before Dragonfly, I was the CTO and co founder of two successful startup companies with workloads of hundreds of thousands of queries per second. Scaling efficiently is a big part of my day to day job. I was also an engineer at Google for a few years where I experimented with many scaling techniques. So today I would like to share my experience with you. If I'll tell you that I have a magic technology that allows you to support a million customers or queries from a single instance with 32 CPUs, you would probably say, why take one? Let's deploy 32 smaller instances and achieve the same. In the last 20 years, we are conditioned to thinking like that. But let's think of it again. We prefer running and supporting 32 smaller instances rather than a single instance. In what world is this possible? So today I would like to challenge this and talk about the benefits of vertical scaling first, and especially on the cloud. Let's begin with some history. In the 1990s, scaling was a real issue that required very expensive hardware. Yahoo was holding big chunks of the internet on a few big computers. But then came Google and created an index of the entire internet with many commodity instances. This required building a completely new software stack to support horizontal scaling. So Google created a distributed file system called GFS and a MapReduce techniques to traverse and update the data on GFS, and Bigtable as a structured storage on top of GFS, and many other software tools. Following the Google success, the entire industry started thinking in terms of horizontal scaling, microservice architecture, etc. In 2006, Amazon introduced its AWS cloud. Right in about the same time, hardware companies were struggling to deliver on Moore's law in its traditional form and started introducing multi-core CPUs. So nowadays, we have cloud instances with 100 CPUs and 1 terabyte of memory, but they're running 100 tiny processes of the same service. In other words, we live in a world where we are building horizontally scalable software on a vertically scalable hardware. Is that really efficient? Let's take a look at such cloud hardware. An AWS C7 has 64 CPUs and 128 gigs of memory. Most of us here are not even planning of using a bare metal instance like that. We are trained to think that running with many small instances is the right way. We imagine that we are getting a dedicated instance for each, but actually on the cloud, we are getting a few tenants on the same bare metal instance. So what's wrong with that? Is that an issue? First of all, it means that we are wasting resources. Resources like duplicated memory, we need to run 64 operating systems and 64 Prometheus agents and 64 of our own process. In many cases, my 64 small instances need the same in-memory data. So the entire memory is duplicated 64 times. In other architectures, we need to perform RPC calls to retrieve the data instead of running an in-process function call. So right from the design phase, the software we make today is more wasteful and less performant. Now, we are not running alone on those cloud machines. There should be perfect isolation between the processes because on the cloud, the tenant next to me might belong to a completely different company. And indeed, you're getting a dedicated CPU and dedicated memory resources. But what about the network? A C7 instance has 30 gigs of network. According to the same spec, a C7 medium has 1.25 gigabytes of networking. So if we multiply it by the amount of C7 mediums that we can fit on a bare metal, we would get to 80 gigabytes of network. But we know that on this bare metal machine, we have only 30 gigabytes of network. So this means that cloud instances are actually overcommitting on networking. So we ran an experiment using Redis. When the host is not loaded, a single process can deliver 153,000 requests per second. But when the same machine has noisy neighbors, it can only deliver 18,000 requests per second. So we are expecting to get from a bare metal machine with 64 processes like that 5 million QPS, and we are actually getting only 10% of that. This is not a bad luck, this is a bad design. To prevent it, you should be the big fish on the instance and not the small one. Now let's talk about our own traffic load. We all handle traffic load by provisioning and auto-scaling. We assume that all machines are getting the same load. But in fact, the distribution of load is not perfect. Actually, the variance is proportional to the number of nodes in the cluster. So with 8 shards, the hottest shard is getting 2% more load than the average one. But with 64 shards, it's getting 20% more load. So again, more shards means that you have to be more provisioned on every shard, and the total infrastructure efficiency drops. And load is also distributed with time. Day and night traffic are different, right? In this example, think of a call center with an average of 100 calls per second. But because the calls are distributed over time, we need to plan the capacity so queues will not be formed. Queues means more latency, and latency means better reputation for our call center and business. So in a very simplified way, and according to the golden rule, if I expect to have 100 concurrent calls on average, I need to provision a total capacity of 110, which is 10% provisioning, not too much. The 10 extra agents comes to protect our business from the inflection in traffic. But what if I decide to split the workload into 100 different small call centers? So each call center should get an average of a single call per second. And according to the same formula, L equals 1, and the square root of L also equals 1. So the number of agents in each call center should be 2. And the total agents in 100 centers should be 200. So this is an extra of 100 agents, just because we decided to split the workload. A 10% provisioning became a 100% extra provisioning. In our case, we don't use agents, we use CPUs. So as a recap, splitting resources is not efficient on cloud workloads. It's more efficient to build and maintain vertical scalable solutions. And this is even before we start talking about the simplicity of monitoring and maintaining of big shards versus many small ones. So it's not that I'm saying you should not do horizontal scaling. Even the perfect vertical solution will eventually hit physical limitations and will need to scale horizontally. But if you care about simplicity, if you need efficiency, on the cloud, vertical scaling should always be your first choice. And if you do need to scale horizontally, I still suggest that you do it with bigger and stronger shards. This is what we are doing at Dragonfly. Dragonfly is the most efficient data store for cloud workloads. It's a drop-in Redis replacement that can deliver more than 4 million QPS from a single instance. The magic for this amazing performance is in Dragonfly's ability to scale vertically with the cloud instance. If you would like to boost your infrastructure performance, so visit our website at dragonflydb.io or our GitHub project. And in case you have any questions or comments, feel free to contact me directly. And I hope that you enjoy my talk and that I managed to challenge your opinion about scaling. Bye bye.